So same as I'm trying to predict some target variable X. So it's generally called as a D, desired output. This is the desired output. This column is called as the desired output. I'm trying to calculate, I'm trying to predict this output variable X or target variable X based on the three input features A, B, and C. Just explanation, I'm taking this type of data sets. You can use any in place of this data. Okay. Now I am choosing a model. So this is my ANN model. I want to use to predict the variable X. This is my ANN model to predict the variable. That predicted variable I'm calling it as a O or OK, output of the kth layer. So this is my output layer and this is my input layer. So this is represented with I input layer, J hidden layer, K output layer. So number of neurons in my output layer equal to 1 because I'm trying to predict only one variable X. The number of neurons in my input layer I, that is the 3 because I have the 3 inputs that is called A and B and C. Okay. So now between the input layer and output layer, we have the hidden layer. So the number of neurons in the hidden layer is a random number. So we have to tune that number of neurons in the hidden layer. Okay. So that's why, just for example, I'm considering the 1, 2, 3, 4, and 5 neurons in the input layer. So for every neuron, I'm taking the linear activation function as of now. Now all the layers should be fully connected. So fully connected means the input layer, every input neuron should be connected to the all the hidden neurons. Similarly, this input neuron should be connected to the all the hidden neurons. And this input neuron again should be connected to the all the hidden neurons, the fully connected. Similarly, every hidden neuron should be connected to the output neuron. And the weights for every connection is a W, J, K between the jth layer and kth layer. And the weights between the input layer and hidden layer that is called as the W, I, J. So the same as what we considered in the previous case. Now I want to add the bias parameters also. Generally, bias parameters are added to every neuron in the input layer and the output, in the output layer and the hidden layer. That means, so I want to add one bias parameter. I can call it as a BK, bias parameter BK to the output layer. So for a bias parameter, your input always 1. Input is always 1. This is the one bias parameter I'm adding. I'm trying to increase the complexity of the model. Similarly, the number of neurons in the hidden layer equal to 5. Every neuron will have the one bias parameter. So that's why I can write like this. So this is like a B1 and this is the B2 and this is the B3 and this will be B4 and this will be B5. So these are called as the bias parameters. For every bias parameter, the output equal to 1. So number of bias parameters is depending upon the number of neurons in the output layer and number of neurons in the hidden layer because every neuron has a one bias parameter. So this hidden neuron has one bias parameter B1, this neuron has one bias parameter B2, this neuron has a bias parameter B3, like that. Similarly, our output neuron has a one bias parameter BK. So this B1, B2, B3, B4, B5, I can call all these things as a one variable like a Bj I am representing. Bj means when j equal to 1, that means first neuron B1, j equal to second neuron B2, j equal to 3, third neuron B3, j equal to 4, fourth neuron B4, j equal to 5, fifth neuron B5, like that. So these are the bias parameters. So what are the, if someone asks you what are the total number of model parameters, then I can call what are the number of weights. Number of weights are the input layer neurons are 3 multiplied by hidden neurons are 5. So these are the total number of weights in the Wij plus hidden layer 5 and input layer 1, 5 cross 1. So this is the further weights. So total number of weights equal to 3 into 5, 15 plus 5, 20. 20 number of weight parameters are there. And Bias parameter. How many number of bias parameter for the hidden layer? 5 bias parameters. B1, B2, B3, B4, B5. Why five bias parameters? Because we have the 5 neurons in the hidden layer. So 5 plus. So number of neurons in the output layer equal to only 1 because we have the only 1 neuron in the output layer. 5 plus 1, that's equal to 6. So total number of model parameters equal to 26. Total number of model parameters equal to 26. Right? So this is my architecture. This is my architecture. So now we have to work on this ANN architecture that has the input layer, that has the output layer, that has the hidden layer, that has the bias parameters for the both hidden layer and also for the output layer. Right? Hope you are clear up to here, right? So now we will move to the training algorithm. Using the backpropagation algorithm, we are going to discuss. As usual, we know that step 1. So what the step 1? You have to read data. So what the data? You have the A, B, C, and X data. And also you have to randomly initialize. What you are going to randomly initialize? You have to initialize the weights, Wij, and also initialize these weights, Wjk, and also initialize the bias parameter, Bj, and also initialize the bias parameter, Bk. So Bj shape is 5 cross 1 because they are the 5 neurons. Bk shape is 1 cross 1 because only 1 neuron in the output layer, right? Whereas the Wij shape is Wij between the input and hidden. Input neurons are 3, hidden neurons are 5. So the shape is 3, 5. Wjk, so hidden and output. Hidden neurons are 5 and output neurons are 1, 5 cross 1. So these are the size or shape of the every matrix of the weights and the bias parameters. After completing this step, you have to initialize the learning rate as a 0.1 and also you have to initialize the number of epochs as a 100 like this. You have to initialize. Okay. So now, so what next? So after step 1 or the initialization. So next we are moving to the step number 2. So what we are going to do in the step number 2, we have to set iteration equal to 1. And step number 3, we have to set our sample number equal to 1. And in the step number 4, we have to do the predictions, forward population. Step number 4 is nothing but we can call it as a forward pass. Forward pass. So forward pass is nothing but the calculation of the predictions. Predictions is nothing but your outputs of the hidden layer, outputs of the output layer. Output of the output layer is nothing but your final prediction of your neural network model. So we are going to find the OJ and OK. How we calculate the OJ? Anyone tell me how we can calculate the OJ? So OJ nothing but because I am using the linear activation function, whatever the input is, the same is the output. So what is the input for the hidden layer? So input for the hidden layer equal to your Wij multiplied with your inputs and add the bias parameters also. So OJ equal to, we discussed yesterday, OJ equal to Wij multiplied by your input values A, B, C, plus you have to add your bias parameters of the hidden layer. And how we can calculate the output of the output layer, OK, or output of the kth layer. So output of the kth layer equal to, this is the OK I want. If you want the OK is nothing but because I'm in the linear activation function. So OK is nothing but the input of your output layer. OK is nothing but the input of your output layer. Okay. And how we can calculate the input of the output layer? That is you have to multiply over this weight matrix with the output of the hidden layer, right? And you have to add the bias parameter of the output layer as well. So how we can get this one? OK equal to Wjk into output of the hidden layer Oj plus bias parameter Bk. This is the Oj and OK. So after completing this part, now we have to concentrate on the derivation. So derivation means what is the error? Error equal to 1 by 2 minus your desired output minus actual output whole square. Now I want to calculate change in weights between the input and output, hidden, change in the weight between the hidden and output, change in the bias parameter at the hidden layer, changing the bias parameter in the kth layer or the output layer. These four expressions I need to derive. These four expressions I need to derive. Right? I hope everyone is following. Okay. So how we can calculate the WJK first? How we can calculate the WJK? So delta WJK equal to, based on the gradient descent algorithm, minus eta into dou E by dou WJK. So minus eta into dou E by dou WJK can be written as dou E by dou OK, dou OK by dou WJK. Both are same, right? So this can be written as minus eta dou E by dou OK. These two come forward, two cancel. So you have the dk minus OK. And here we have the negative sign that moves forward, then it becomes a plus. Now dou OK by dou WJK. Here OK is available. So what is the dou OK by dou WJK? You have the OJ expression. Simply, it is a OJ. So this is the expression for the delta WJK. Now calculate the delta Wij. Calculate the delta Wij. So delta Wij equal to minus eta into dou E by dou Wij, based on the gradient descent algorithm we discussed in the first day, day 1. Now this is equal to minus, you can write further, minus eta into dou E by dou Wij can be written as dou E by dou OK, dou OK by dou OK by dou OJ, and dou OJ by dou OJ by dou Wij. So then both are same. Dou minus 18 dou E by dou Wj nothing, but this one cancel, this one cancel. Finally, dou E by dou Wij. Both are same. Now you can see minus eta dou E by dou OK. Dou E by dou OK means 2 forward, 2 to cancel. Here minus negative sign, it will become a plus. So you have the dk minus OK. And dou OK by dou OJ. Here it is the OK. So dou OK differentiate with OJ, then you have the WJK, right? Next, dou OJ, dou W. Dou OJ differentiate OJ with respect to Wij, then you have the ABC values. So this is the expression for delta Wij. So you have to remember all the things while coding. So this is the delta Wij expression. And this will be the delta WJK expression. But we need to calculate delta WBK and delta WBJ. That also we need to calculate. Okay. How we can calculate the delta WBK? So delta BK equal to minus eta into dou E by dou BK. Why every time taking the E? Because this is my error function. I am trying to minimize this error function. So as per the gradient descent algorithm, we have to calculate the gradient of error function or gradient of objective function with respect to its variables. With respect to its variables. So that's the dou E by dou OK. Okay. So if it is a dou E by dou OK, so minus eta dou E by dou BK. Sorry, dou E by dou BK can be written as dou E by dou OK and dou OK by dou BK. Both are same, right? So minus eta dou E by dou OK, 2 come forward, 2 to cancel. So you have the dk minus OK, but OK coefficient is minus 1, it becomes a plus. Again, dou OK by dou BK. So dou OK by dBK. So OK differentiate with respect to BK, you have the 1. That's it, only 1. That means, so this is the expression for your delta BK. This is the expression for your delta Wij. This is the expression for your delta WJK. You have to remember all the things we'll write in the code. Okay. So next part is delta W. Sorry, not delta W. Sorry. Next part is So delta Bj. So delta Bj can be written as minus eta into dou E by dou Bj. So that's equal to minus eta into dou E by dou Bj can be written as dou E by dou OK and dou OK by dou Oj and dou Oj by dou Bj. So both are same. You can see this OK cancel, Oj cancel, dou E by dou Bj. Both are same. So that's equal to minus eta dou E by dou OK. What is the expression? Dou E, error, go back to error function. So our error function is this one error function. Differentiate this error function with OK. 2 come forward, 2 cancel. Then we have the dk minus OK. Where OK coefficient minus 1, so it becomes a plus. So it will become a plus, and here we have the dk minus OK. Now dou OK by dou Oj. Dou OK by dou Oj. Then what is the differentiation here? That is the Wjk. Now dou Oj, dou Bj. Dou Oj with Bj, that's nothing but the only 1. So finally, so delta Bj can be written as delta Bj, change in bias parameter on the hidden layer, equal to eta into dk minus OK into Wjk. So this is how we can find the change in bias parameters in the hidden layer, change in bias parameter in the output layer, change in weights between the input layer and hidden layer, and also change in weights between the hidden layer and output layer. So now I will use these formulas while writing the coding algorithm. Now step number 5 is to find the change in weight between the hidden layer and output layer, that is the eta into dk minus OK into Oj. And similarly calculate delta Wij, that's equal to eta into dk minus OK into Wjk into your input vector ABC, input sample. And similarly delta Bk equal to eta into dk minus OK. All the things we derived just now. That's why I'm directly writing the expressions. And again delta Bj equal to eta into dk minus OK into dk minus OK into Wjk. Dk minus OK into Wjk. Right? So this is the how we are finding the change in weights, change in bias parameters. So training is nothing but the updating the weights. Updating the weights means you have to find the change in weight. So next is the step number 6. In the step number 6, we are going to update the weight parameters. How we will update the weight parameters? That is the Wij equal to Wij plus delta Wij. So Wij means initial weights. Now add this change in weights. Then like that your weights will be updated. Like this your weights will be updated. And similarly, Wjk equal to Wjk plus delta Wjk. So delta Wij available here. And these are the initial weights. So you have to add, then updated weights will be coming. Similarly, you can write Bj equal to Bj plus delta Bj, update your bias parameters of the hidden layer. Bk equal to Bk plus delta Bk, update the your bias parameters of the output layer as well. You have to update both. So next step is step number 7. Next step is step number 7. So step number 7. So step number 7 is once the weights are updated, what will be the next step? So we have to update your sample number. Sample equal to sample plus 1. So what will be the step number 8? As per the back propagation algorithm, step number 8 is you have to check whether your current sample number is greater than number of samples that you started. In your training data, you have some samples, right? Whether you covered all the samples or not. If it is greater than, if the current sample number greater than the total number of samples in the training data, true means you are covered all the samples. False means still some samples are left in the training data to use. If it is true, then go to the next step. If it is false, then go to your step number 4. Go to step number 4. Again, with that new sample, you have to find the predictions. You have to calculate the delta W, delta Wij, delta Wjk, delta Bj, delta Bk, and you have to update the weights and the bias parameters. Now, let's assume you have covered all the samples. Then what the next step? Step number 9. you have to update your iteration count. Iter equal to iter plus 1. You have to update your iteration count. So now step number 10, check whether your current iteration value is greater than number of epochs or maximum number of iterations you mentioned at the time of the initialization. If it is a true, that means you covered all the iterations that you mentioned in the first iteration, initialization. If you said epochs equal to 100, whether you run this algorithm 100 times or not. If you are running the 100 algorithm 100 times, true, then go to the next step. If it is less than 100, iteration is less than 100 or equal to 100, then it is like a false. Then you go to step number, again, go to first sample and do the complete process from the first sample, second sample. We discussed already yesterday. So go to step number 3. So what is the next step here? Next step means step number 11. So here nothing but the save your model. So training was completed. Simply save your model. Save your model means you have to save your weights and the bias parameters. And also you save the bias and weight parameters, then calculate the training error and also calculate the testing error using the training data and the testing data. If these errors are less and you are happy and your client also happy, then what you have to do is simply deploy your model in the back end of your application. That's it. So finally you have to stop this process. Step number 12 is finally you have to stop it. So this is the complete process. Okay. So this is the complete process for the ANN thing. So I want to draw the flowchart for this one as well. So later we will try to implement the parting. Okay. So coming to the flowchart, so start the algorithm. So what are the steps now? So read data. What are the data? Input values and your output values as well. And randomly initialize. What you are trying to initialize? You have to initialize your weights, Wij, Wjk, initialize bias parameters, Bj and Bk. Also set your learning rate as a 0.1. That is your choice. You have to set any value eta between the 0 and 1. I'm choosing the eta equal to 0.1. I'm using the only stochastic gradient descent optimization. Actually, there are many variants of the gradient descent algorithm. In such cases, the eta will be changed during the iterative process. That we are not covering as part of this FDP. This is the first FDP that we organized. So as of now, we fixed the learning rate as a 0.1 and number of epochs you can choose as a 100. So this is the first step. So what is the next step? So next step is once you initialize all the things, so calculate the outputs. So outputs means OJ, you have to calculate OJ forward pass. This is called as forward pass. OJ equal to Wij into your inputs ABC and add the bias parameter. Similarly, calculate the OK equal to Wjk into your output of your hidden layer, because output of the hidden layer is input to the kth layer or the output layer, plus your bias parameter in the output layer or in the kth layer. So this is the prediction calculation. Generally, this part is called as the forward pass in the back propagation algorithm. This is called as the forward pass. This part is called as the forward pass. So after that, what we have to do? We are calculating the OJ, all the things, right? So after that, we have to calculate delta Wjk. We have to calculate delta Wij. You have to calculate delta Bj. You have to calculate delta Bk, right? So how we calculate all these values? We already derived, right? Delta Wjk equal to eta into dk minus ok into Oj. Delta Wij equal to eta into dk minus ok into Wjk into your input vector. And delta Bk equal to eta into dk minus ok. And delta Bj equal to eta into dk minus ok into Wjk. Okay. So this is my complete change in weights expression, right? So after calculating the changing weights expression, so our next step will be updating the weights and bias parameters. How we update the weights and the bias parameters? Wij equal to Wij plus delta Wij and Wjk equal to wjk plus delta wjk, and bj equal to bj plus delta w delta bj, and bk equal to bk plus delta bk. So this is how we are going to update your model parameters. Actually, this whole part, this part and this part is called as the backward pass. Backward pass. So this is called as the backward pass. This is called as the forward pass. The completely is called as the back propagation. This complete part is called as the BPA, back propagation algorithm. Okay. These three steps will be repeated. These three steps will be repeated. So after updating our weights and the bias parameters, so our next step will be, after updating the weights and the bias parameter, our next step will be, you are going to the next sample. So sample equal to sample plus 1. Now here we are checking whether your sample number is greater than number of samples in the training data or not. If it is yes, you are going to the next step. If it is no, where to go? If it is no, that means still few samples are left in the training data. Then you are going back. You are going back to You are going back to your prediction calculations. Prediction calculations. So let's assume if you cover all the samples, that means your sample number is greater than the training samples. Then what we have to do here? Here we are going to update your iteration count. Iter equal to iter plus 1. Update your iteration count. So once you update your iteration count, now check whether you covered all the iterations or not. That means if the current iteration number is greater than the epochs, max number of iterations or not. It is not, then you go to, again. So I forget one thing. Here you have to take one more thing. Here you have to set sample equal to 1. Now, if the number of iterations is not completed, then you go back to the first sample again and do the process repeatedly. So this is the two for loops we have to use in your algorithm. So outer for loop is for iterations, and inner for loop is for the samples. Inner for loop is for the samples. Right? So finally, suppose if it is S, that means you are covered all the 100 epochs. Initially set epochs equal to 100. You train the algorithm for the 100 epochs. Then this decision block will be S. Then what you have to do? Save model. So save model is nothing but the save Wij weight, Wjk, Bj, and Bk. All the model parameters you have to save. After that, calculate your training error, and also you have to calculate your testing error. If these two errors are good, if it is properly trained without any underfitting problem or without any overfitting problem, then you can simply deploy your model. If you and your client are happy with these errors, so then deploy your model. So that's it. With the deploy your model, you can stop this complete process. So this is the complete flow chart for train back propagation algorithm. Flow chart for a back propagation algorithm for the back propagation algorithm for the ANN model by considering the input layer, output layer, hidden layer, weights, bias parameters, and linear activation function. So this is the complete flow chart. Okay. So hope you understand this complete training algorithm, back propagation algorithm for this ANN. But still it is not a perfect complex ANN model. Slowly we are increasing the complexity of the model. Initially we consider only input layer and output layer with only weight parameters, with only linear activation. Later we increase the complexity by adding the bias parameter. Later we increase the complexity by adding the nonlinear activation function. Later we increase the complexity by adding the hidden layer. Later we increase the complexity by adding the hidden layer and the bias parameters. But even though we are including the hidden layer, but still I am using the linear activation function only. But it is not a good choice to use the linear activation function for a ANN model for the complex problems. So we have to go for the nonlinear activation function only. But that part we will discuss later after programming implementation. Okay. Now we are trying to discuss about this implementation of the whole algorithm in the Python. So ANN with hidden layer, with linear activation function, and also with the bias parameter. Done. So this is my data actually. This is the data. So I have the three input features A, B, C. And with these three input values, I am trying to predict the variable X. So don't confuse. This is the data, a small sample data I am using to explain the models. In place of this data, you can use your data. Whether you are working on the temperature prediction, you can use the temperature data. If you are working on the load prediction, you can use the load data. So based on your problem statement, you can use the data in place of here. I am taking the generalized small data for the workshop purpose, for the FDP purpose. So that you can easily understand. Now coming to the data import, the whole data is available in my Google Drive in NN data folder with the name of sample data 2. So from this Excel file, I read the Excel data and stored in this variable, Okay. So this is the data. What I'm seeing here, the data is available with a variable called data variable. Okay. So as we know, same steps, because that's why I'm moving somewhat further, because from the yesterday session 1 till now, few steps are repeated. That's why I'm moving fast. Okay. Okay. So now coming to the data split. So data split is nothing but we are trying to split the data for the training purpose and also for the testing purpose. So if you want to split the data for the training and testing purpose, we have to use the method or a function called train underscore test underscore split. This train underscore test underscore split will be used to split our data as a training data and also as a testing data randomly. It will split the data for the training and testing purpose. Generally, what we are doing in our class. When you are delivering one subject to the students, if I have a 20 problem set, I will not demonstrate all the problems in the classroom. I will demonstrate maybe 5, 10 or 15 questions in the classroom. And I will keep remaining set of questions for the test, for examination purpose to test the students. Here also, whatever the data you have to split the data for the training of model and also test the model. Here data is nothing but your original data. Test size is nothing but what is the size? Test size. That means 0.05 means 5% of data I want to use for the testing purpose, and remaining 95% of data I want to use for the training purpose. Okay. So these things we repeated, same code we are using. That's why I'm going further. So next step is, after data split, our next step is we have to randomly initialize the weights and the bias parameters. Okay. You can see our flow chart. Randomly initialize Wij, Wjk, Bj, and Bk. All the weights and the bias parameters should be initialized randomly. Okay. So how that part now we are going to discuss now. So random initialization, Wij initialization, Wjk initialization, Bj initialization, Bk initialization, right? So Wij, we know np.random.uniform for random initialization. I want to initialize all the values in the range of -1 to +1. You can choose any. Just I'm taking the -1 +1 here. You can take -10 +10, -100 +100, -999 +999, or -999 +88. Your choice. You can choose pick some random values from some set space. Now for the Wij, why I'm keeping the 3, 5? Because my Wij is in between. Where it will be located? Wij is located between the input and hidden. Input neurons are 3, hidden neurons are 5. That's why it's the 3 cross 5. But why Wjk equal to 5 cross 1? Wjk is between the hidden and output. Hidden is a 5, output is a 1. So 5, 1. And why Bj equal to 5, 1? Because every neuron in the hidden layer and output layer has a bias parameter. Because in the hidden layer, I have the 1, 2, 3, 4, 5 neurons. So 5 bias parameters are there. That's why it's the 5, 1. And Bk equal to 1, 1, because in my output layer, I have the only one output neuron. I have the only one bias parameter. That's why I take the 1, 1. So based on this code, like this, we are going to initialize all the weights and the bias parameters. We have to initialize all the weights and bias parameters. So after initialization, so after initialization, so what's our next step? So after initialization, if you go to our flow chart, after initialization, we are going to do the forward pass. Forward pass means predictions to predict the output of the your hidden layer and predict the output of the your output layer. So forward pass function is already created. This is my forward pass function. For this forward pass function, what is required? I require the data. I require the Wij. I require the Wjk. I require the Bj. I require the Bk. Right? So I require the data. I require Wij. I require Wjk. I require Bj. I require Bk. So this prediction will be done for every sample, right? For every sample we have to do. See, for every sample we are doing. That's why J is nothing but the sample number. So J is nothing but the sample number. So now how we calculate the Oj value? You can see Oj equal to Wij into your input vector plus your bias. That's what I'm doing here. Oj equal to, it's the matrix multiplication of your input vector. Input vector means A is the data set, right? Input vector, what is the input vector? You can see here, your input vector is the first 3 columns. So that's why I'm taking the first 3 columns. That is multiplied with Wij, Wij and add Bj and add Bj. So that will give the output of the hidden layer. Similarly, if you want to calculate the output of the output layer, OK equal to np dot dot, that is a matrix multiplication between Wjk into Oj, Oj into Wjk plus we have to add Bk plus Bk. That's it. So this is the forward pass function. So I'm creating one function, forward pass function, to calculate the output of the hidden layer and also output of the output layer. Okay, output of the hidden layer and output of the output layer. So after that, backward pass, right? So this part is called as the backward pass. In the backward pass, what we have to do? We have to calculate the change in weights, delta Wjk, delta Wij, delta Bj, and delta Bk. So you can see here, in the backward pass, if you want to calculate the delta Wjk or delta Wij, what required? Eta required. So this is the learning rate, eta. Dk, OK required. Dk means actual data. That is the A. And OK required. This is the OK. And what else required? Oj required. So this is the Oj. And you required Wjk. So this is the Wjk. And you required so Bj and Bk also required to update. See, you can see here Bj equal to Bj plus delta Bj, Bk equal to Bk plus delta Bk. So Bj, Bk also required in the backward pass. So all the parameters we have to pass to this function. The backward weight updation BP, back propagation. In the back propagation or backward pass, we are updating the weights. Okay. Now, so see, you can, if you observe this weight matrix, what the size of the weight matrix Wij? Size of the weight matrix Wij is 3 rows and 5 columns. 1, 2, 3, 4, 5 columns. So when you are updating, we have to update the every point, right? Every point you have to write. You have to update the every point. So that means your delta W also 5 values like this. Then only you are able to add, right? This is the Wij plus delta Wij. So this is the 3 cross 5. This is also 3 cross 5. So you have to calculate the delta Wij, the 3 cross 5 matrix, and add to the original vector or original matrix. Then you will get the updated weights. Okay, so that's why initially I will initialize this delta Wij matrix. I will try to initialize this delta Wij matrix. So I want to initialize this delta Wij matrix with all zeros. Later I will update. So just I am updating the delta wij, 3 cross 5. Why 3 cross 5? 3 rows and 5 columns. Why 3 rows and 5 columns? Because wij between the input and hidden. Input is the 3 neurons, hidden is the 5 neurons. That's why it is a 3 cross 5. And delta bj or dbj nothing but the number of changes in the bias, because you have the 5 bias parameters in the hidden layer. So your changes delta b is also 5. Okay. How we calculate the delta wjk? We have a formula we already derived. How we calculate the delta wjk? Eta into dk minus ok into oj. That's what here. Eta learning rate. This is the desired output in the third column. dk minus ok into oj. The matrix multiplication that will give the delta wjk. So delta wjk equal to matrix multiplication between eta into desired output minus predicted output and your output of the hidden layer as per our derivation. Now once you got the delta wjk, now update the weights. Wjk equal to wjk plus delta wjk. So wjk equal to wjk plus delta wjk. For the matrix proper addition, proper dimension, maintenance of the proper dimensions for the addition purpose, I am taking the transpose. Right? So once you calculate the wjk, update the wjk, now I want to find the delta bk. How we calculate the delta bk? Delta bk equal to eta into dk minus ok into, that's it, 1. Eta into dk minus ok. So delta bk equal to eta, that's the learning rate, into this is the desired output d minus ok. So that also completed. Now update your bias parameter of an output layer or kth layer, bk equal to bk plus delta bk. That's completed, right? Now move to this part. So wij updated and bk also updated. Now I want to update the wij and also bj. This part I want a backward propagation, right? In the forward propagation, we are going forward and calculate the output. In the backward propagation, first update the weights in this layer and bias here, and move further and update the weights here and the bias here. So there's a forward pass and the backward pass. So this is the part which is used to update the weights in the input layer and hidden layer and the bias parameters in the hidden layer. So we know the formula, right? wij equal to eta, wij equal to matrix. This is completely matrix multiplication. So np dot matrix multiplication of eta, that is called learning rate, dk minus ok. So this is the desired output minus ok predicted output into wjk and input vector a, b, c. So this is my input vector. Why it is a 3? Why it is a 0 column 3? It is a 3 because I want to take the third index column. Third index column means you can see the data. This is the 0 index, 1 index, 2 index, 3 index, third index column. This is the output. So that's why it's the 3. But here it is the input. Input is 0, 1, 2. All are required. That's why from 0 to 3, but 3 is excluded. So 0, 1, 2, all 3 values we have to take and multiply. It will give your delta wij. Similarly, if you cross check your delta bk, where it is, if you cross check your delta bk, not delta bk, delta bj, so delta bj equal to, eta into dk minus ok. So this is the desired output last column minus my predicted output ok multiplied by wjk. And once you got the delta wij and delta bj, now update wij equal to wij plus delta wij, bj equal to bj plus delta bj. So this is the backward pass to update the weights and the bias parameter. That's it. So in the forward pass, we are going for the prediction. In the backward pass, we are going for the updation of the weights and the bias parameters. So training completed. Not completed, just we are write a code for the functions. like a forward pass function and a backward pass function, weight updation function. Now we are going for the training. So in the training, if you go to our algorithm, our flow chart, we have to initialize the eta 0.1. So just I am trying to learning that eta as a 0.1. And number of epochs equal to 100. So set number of epochs equal to 100 and call these epochs here. Call these epochs here. And why I'm taking the Q1? Because training, we require the training sample. So training samples are available with the Q1. Data train, that the training data samples are available with Q1. Test data samples are available with the Q2. Okay. So Q1. Now what we will do? First we will do the forward pass. So just I'm calling the forward pass function. Next we have to do the backward pass. Just call the backward pass function. So combination of these two is called as your back propagation algorithm. That's it. So this process will be repeated until you reach all the 100 epochs. So this is the complete training algorithm. But some code is available here as the functions. So I'm creating a functions as the forward pass and the backward pass, and those functions I'm calling here. Those functions are I am calling here. So just simply run this. Okay. So training was completed. So actually, these are my initial weights, minus 0.41, something like this. But after training completed, these are my updated weights. These are my updated weights. So training was completed. Now what's the next step? How we observe the performance of my neural network model? How we observe the performance of my neural network model? That is based on the training error and based on the testing error. Based on the training error and based on the testing error. So we are going to find. Okay. So now coming to the, if you want to find the training error and testing error, first calculate the prediction using the test data and compare that prediction with the actual data, actual values in the test data and find the error. Similarly, if you want to calculate the error on the training data, find the predictions using the updated weights and the bias parameters using the training data and compare this prediction with the actual data available in the training data and compare and give the error. That's called training error. So if you want to calculate the testing error or if you want to calculate the training error, first you have to do the predictions using your updated ANN model, using your updated weights and the bias parameters. Okay. So predictions is nothing but which function we will use for the prediction purpose. For a prediction purpose, which function we will use? We will use the forward pass function for the predictions purpose, OJ and OK. So simply I am using the forward pass function and I'm taking the Q2. Q2. So it's a small wrong. Yeah, Q2. Okay. Q2 is the test data. Q2 is the test data, right? So I have to pass the test data. With the test data passing to the forward pass, it will give the both OJ and OK. I want only OK. Predictions of model is nothing but the output of the output neuron, not the output of the hidden layers. So I want only output of the output neurons. Output of the output neurons are available with this is called OK. So I want this part, not first part. That's why in the first part I'm keeping the underscore. Only I want to capture this information. I want to capture this information. That will give the predictions. And similarly, output predictions with the training data. Output predictions with the training data. So training data, so I am taking the Q1. I'm taking the Q1 because I want to go for the prediction. So go for the forward pass. Okay. In the forward pass, it will give the two values. One is the predictions of the hidden layer and predictions of the output layer. Actually, I want the predictions of the output layer, not input layer. That's why the hidden layer part, I kept underscore. I don't require those predictions of the hidden layer. I want the predictions of the output layer. So those values will be stored in pred underscore train. So this will give the predictions of the training data. Now, if you want to calculate the errors, how we calculate the error? We discussed all the things. That's why I'm moving fast. So mean squared error, mean squared error, mean squared error. You have to call from the scalar dot matrix. You have to call the mean squared error method. And for this method, pass the actual output and predicted output. Then it will give the error between these two as a mean square error. Also pass training actual output and training predicted output. It will give the test training mean square error. So I'm happy. I'm getting the error 0.002 and also training error 0.0009. So errors are almost close to zero. Let us do myself, my client also happy. Then directly deploy. This is the deployment code. This is the code for the deployment. Okay. So in the code, what I am doing, just because we have the three input switches. So I am asking the, based on this code, I am asking the user enter the three values, A value, B value, and C value, and all the three values stored in this input vector. What are the input vectors are A, B, C values? Those values are passing to the forward pass function because the forward pass function gives the actual predictions. Forward pass will use to get the predictions, right? So I am giving the forward pass. So we can run this cell. Now we will work with existing data otherwise. So you can take any sample from your data. I will take 0.1, 0.2, 0.3. I'm expecting 3.56. Okay, see whether we are getting or not. So 0.1, 0.2, and 0.3. And you can see the output 3.51. So my data is 3.56. So almost equal. So my model also predicting 3.51 and actual value is 3.56. Both are almost equal, right? So this is how, why you may have a question, how it is predicting near, that is our motto. Our algorithm motto is the algorithm should update the model parameters like weights and the bias parameters in such a way that the prediction of your model should be more close to your output values. If that is the case, then your errors will be very small, then your model is perfectly working. Then you can deploy it. If the errors are zero, if errors are very small, then only your application will predict the value more close to the actual values. If the errors are very large, if you deploy the application, if you deploy that model in the application, then your application will not give the correct values. Your application will not give the correct value, right? Hope you understand, right, as of now. So this is the whole thing about the neural network models, ANN models training course. Still, it's not completed. So still now initially we started, so I want to stop sharing.